Hello and welcome back. Here I am going to explain you the experiment on finding out the wavelength of a laser. So here we have a diode laser. Then in front of diode laser we have a diffraction grating over here, and we have a screen. So with the help of this experimental setup, we are going to find out the wavelength of the given given laser. Okay, so just I will draw the experimental setup here for determining the wavelength here. So first of all, we have a laser beam here. So this is the laser. Then we have a grating. So this is the grating, and then on the screen, so on this screen, this is grating, and we have this screen here. So on screen, this we will get the central dot, and then there will be a first order diffraction at an angle of theta on both the sides. Then there will be a second order diffraction on both the sides, like this. So we will measure this distance. This distance we will call it as capital D, and this distance we will call it as what? Small d. So rather we will take average of these two distances here. Maybe this distance we will call it as a D1 and this as a D2, and then we will take average of 2. Ideally, if our experimental setup is in a proper way, then D1 and D2 should be same. So while writing, I will write down it as a D and this also as a D. Okay. Now we will just briefly see about laser as well as the grating. So a laser is nothing but what? Its full form, laser, is light amplification by stimulated emission of radiation, by stimulated emission of radiation. So basically, laser beam as compared to our normal light, it has got so many different properties which are very much helpful. So these properties are nothing but, say, they are highly monochromatic. They are highly monochromatic. Means they will have a single wavelength. For example, if we have a red laser, then it will have that particular wavelength only. Say, for example, for a diode laser, it will be say of red color, it will be say around 6500 or so. Then it will have that particular wavelength only and not much broader wavelength spectrum. Say for normal light, we will have a broader spectrum of intensity versus wavelength. Say like this, for normal light. Say maybe yellow color, any color, say for example sodium lamp, etc. But for laser, this spectrum becomes very narrow here. So although monochromatic means not exactly the one wavelength, but it will have that concentrated wavelength intensity at that particular wavelength only. Therefore, they are highly monochromatic, they are highly coherent, and also they have got high power. Okay, so depending upon the power of the laser. So due to these fantastic properties, they have got so many applications. Like a laser beam can be made incident on moon surface and it can be reflected back, and with the help of this we can find out the distance between earth and moon. Then it has got so many other applications, like in industry it can be used to cut the metal sheets even, and also to cut the fabrics very precisely. And in medical field also it has got so many applications, like in eye surgeries, then in case of kidney stones and so on. there are so many applications of these lasers. So this is the laser which we are going to use here. This is a diode laser. In the experimental setup you can see this. Now the next part which we are using here is nothing but a grating. Now what is a grating? Grating is nothing but a piece of glass like this, and there will be a straight line will be ruled here on the piece of this glass such that they are parallel lines and the distance between them is constant. So for example, for this particular grating you can see that there are 15,000 lines per inch. LPI means lines per inch. So there are 15,000 lines per inch. So if you want to find out how much is the distance between the two consecutive lines, so we can use this formula for say in terms of centimeter. You know that 1 inch is nothing but 2.54 centimeter. So therefore, to find out number of lines in a particular centimeters, we can just have this 2.54 divided by, we have to divide it by 15,000. So it will give the consecutive distance between the two lines, and that too in a centimeter. So we have to just divide 2.54 by 15,000. Do you have mobile? Another mobile? Yeah. So I will open the calculator. So I will just do this calculation over here. See, 2.54 divided by 15,000. So it comes out to be 0.123 times 0, and then we have 169, and one more digit I will take, this much. So this much centimeter is the distance between two consecutive lines. That means, say for this particular case, this distance between these two lines, this is our, say we will call it as a small e, and this small e is nothing but what? This much. Now if I want to convert this into power, then what I will do is I will just shift these 3 points over here. So therefore this our E for the small e for this particular experiment is 1.693 into 10 raised to power minus 4 centimeter. So this is the distance between the two consecutive lines here. Okay. Now we have seen this experimental setup as well here. So I will just draw this from this particular I will draw this particular triangle, say for example, with this angle to be theta. So I will draw it over here. So it will be like this. This is our capital D and this is our small d actually. This small d we can call it as a x rather. Okay, I will call it as a x here, because in the experiment we have called it as a x while considering in the lab. So I will call it as a x, and then according to this angle is theta, and therefore by Pythagoras theorem, simply if you do the calculations, this distance we will get is nothing but what? Square root of what? D square plus x square. Square root of d square plus x square. So this is the distance of this for diagonal. Now from here, if you want to find out sine theta from this, then what will be sine of theta? Sine of theta will be nothing but opposite, that is x, divided by hypotenuse, that is square root of d square plus x square. So this is nothing but sine square. This is nothing but sine of theta. Okay, so we will make a table here, and with the help of that table we will measure these distances here. I will show you one reading for this. Yes, so I will write down here the observation table. So we have here serial number, then we have D. Now remember, D is nothing but what? The distance between this grating and the screen. This is D. And then we have this X here, X. Okay, we will measure these two distances and we can find out the mean of that. And then we have to find out square root of what? X square plus D square. And then we will find out sine of theta from here. And then we have formula for lambda is nothing but what? It is E sine theta divided by N. So this is the formula, that E sine theta, small e, sine of theta is equal to N lambda. Now in our case, this E we have already calculated. This is this E is 1.69. Yeah, here it is there. The small e is 1.693 into 10 raised to power minus 4 centimeter, and N is equal to 1 because we are only considering our first order diffraction here, and therefore from this formula we will get our lambda is equal to, since N is 1, so it will be nothing but what? It will be simply E into sine of theta. So lambda will be equal to small e into sine of theta. Now I will show you one reading here, one or two readings we can show, and then with the help of that you can do the other calculations also. So here I will take serial number 1. Now this D is distance between grating and the screen. So this, with the help of this meter scale, I will find out it. So see here, it comes out to be equal to 32 centimeters. You can show it here. It is 32 centimeter. Here it is 32 centimeters. So I will note down this reading here. I will write down it here. So it is 32. It is in centimeters. It is 32 centimeter. Now I will measure this X here with the help of this scale. So this is 13 on this side, and on the other side also I will measure. Yeah, it is 13 only, nearly 13 only on both the sides. So this X we will write down it as a 13. Show the mobile here to do the calculations. Yes, your mobile. Yes, so we will just find out this one, that is 13 square plus 32 square. So it is I will write down it here with the help of okay, I will find out 32 into 32 first. So it comes out to be 1024, and then we have to add 13 plus 13, 13 into 13, so that is 169. So I will add 169 in that. So it comes out to be equal to 1193, and then we have to take a square root of this. Square root find करने का नहीं है इसमें 11. So it will be nothing but what? Square root of 1139. Sorry. Square root of 1193. 1193. And then sine theta will be nothing but x divided by square root of 1193. So this will be x divided by square root of 1193. Then we have to find out lambda. So our lambda will be x. Now x is nothing but 13. So instead of this value, I will put here 13. So our lambda will be nothing but E multiplied by this quantity, that is 13 divided by what? Square root of 1193. So we have to just find out this value. I will just do it here. Do we have this square root of square root function? It's not there. Yeah. Yes, here it is there, square root. So we have to just find out square root of 1193. So 1193. So it comes out to be equal to, this square root is nothing but, I will just do these calculations over here. So we have lambda is equal to E. The value of E is how much? This much, 1.693, rather it is 1.693 into 10 raised to power minus 4 multiplied by, we have 13, and divided by this square root comes out to be equal to 34.539. So I will take it as approximation 54. I will take it as approximation 54. So just we have to do these calculations now, remaining things. So it will be yes. So it will be nothing but 1.693 into 13 is this much, and we have to divide it by 34.54. So it comes out to be equal to 6372. I will take this much, and with point here, multiplied by 10 raised to power minus 4 centimeter. So if I want to convert this into angstrom, then you know that 1 angstrom is 10 raised to minus 8 centimeter. Therefore, these four digits will shift towards the right side. So it will be 6372 angstrom unit. So this is the result we got here. And actually this is very accurate result, because for red wavelength, for red light, we know that red color laser, we have around 6300 angstrom unit is the wavelength of red color laser. So which is what we got this observation here. Now what you can do is you can take a multiple readings here just by varying the distance between screen and grating, that is capital D. So you will get different values of X here again, and you can find out these things. So with the help of this experiment, we have done very accurately, we have calculated the wavelength of a red color diode laser as 6372 angstrom unit. I hope that you understand this experiment. Thank you very much, and I am thankful to Sam Gaikwad, Mr. Sam Gaikwad, for helping me in recording this video. Thank you very much.
ये ना
नहीं ऊपर